So to start off section 6.1, we're going to be talking about antiderivatives and integrals. So essentially what an antiderivative or integral is it is the process of reversing what a derivative did. So for instance, if we have a derivative of x squared, well, hopefully by now we know that the derivative of x squared would be 2x. An antiderivative says, well, now that we're given 2x, what happens if we reverse the derivative process? If we go from 2x, we would then go back to x squared. So we need to add a little bit more to that because that isn't technically correct. It's mostly there, but as you'll see in this first theorem, there's a little bit more to it than that. So we say our theorem for antiderivatives says if f prime of x is equal to g prime of x. If you're given two derivatives, then what can we say about the original functions, f of x and g of x? Well, let's think about it. If we were to take some derivative, and I'll just write this off to the side. If we have f prime of x equals 2x and g prime of x equals 2x, they have to be equal to each other, then what does that tell us about the original functions f of x and g of x? Well, can we really say that f of x and g of x are both equal to x squared? Not really, because if you think about it, f of x could be equal to x squared plus 2, and g of x could be equal to x squared minus 8. What's the derivative of f of x equals x squared plus 2? Well, the derivative of x squared is 2x, and the derivative of 2 is 0. So we're just left with a derivative of 2x for f prime of x. And likewise, what about g of x equals x squared minus 8? The derivative of x squared is again this 2x, but the derivative of negative 8 is also 0. So their derivatives are equal, but the original functions are different just by a constant value. Only the 2 and the negative 8 are different. So our theorem says if f prime of x equals g prime of x, then f of x is equal to g of x plus k for some constant value k. Meaning if the derivatives are equal, then the original functions are equal, and all you have to account for is there's going to be some constant value separating them. Okay, remember, just as one quick note before we move on from this, the reasoning for that is when you take the derivative of a constant, no matter what constant you're dealing with, the derivative is always 0 and it goes away, which would make these two derivatives equal. But the original functions, again, are not equal. From here, we can introduce our definition for an indefinite integral, which is the notation that we use to find an antiderivative. So our notation for an antiderivative looks quite a bit different than our notation for a derivative. Remember, with derivatives, we just talked about d dx or f prime of x and things like that. So our notation for an antiderivative or integral is written like so. We call this symbol the integral sign. So we say this is the integral of f of x dx. Let me say that one more time. When you see this long-looking s, we say this is the integral or the antiderivative of some function f of x dx, the integral of f of x dx. And we say that that's equal to capital F of x plus c. We don't have a notation for antiderivative, so we just basically say use the capital letter of what you started with to notate you've found the antiderivative. And then we always put this plus c here because, like we said earlier, when you take a derivative, you could lose that constant. If there was a plus 2 or a minus 8 or anything like that, when you take the derivative, it would go away. So when you find the antiderivative, you have to account for this and say, yeah, there might have been some value plus c that we need to take into account. So with that, we say that, again, this long-looking s is the integral sign. F of x, the function that we're taking the antiderivative of, is what we call the integrand. Dx is the antiderivative is with respect to x. So whenever you see in your antiderivative, this should always come last. Dx, dt, du, dw, whatever it is, this should always be the last thing in your integral. And this letter that comes after the d tells you what variable you're taking the antiderivative with respect to. So just think of it the same way as when we had d dx of x squared. This meant that we were finding the derivative with respect to x. This dx inside of our integral sign tells us we are taking the antiderivative with respect to x. And finally, from here, like I said a moment ago, c just represents the constant of integration. It means the constant that could have been lost along the way when you took your derivative. So now when you're reversing the process, you have to keep in mind that there could be some plus 5 or minus 800 that got lost when you took the derivative originally. It's okay if this is a difficult process to grasp. As we go through the problems, hopefully it will make more sense. The reason why it's so difficult is it's the same reason why multiplying is something that's pretty commonly known, but division is so difficult to grasp because it's reversing multiplication. Well, this is reversing derivatives, so it's always harder to go backwards than to go forward. So with that, we'll introduce a couple more notes and then we can actually get into some examples. So let's do a quick recall. D dx, the derivative with respect to x of x to the nth power. Well, we know to find that derivative, we take our exponent, we multiply it out front, and then we subtract 1 from it, which gives us n times x to the n minus 1. Again, we multiply the exponent out front and then subtract 1 from it. So how would you reverse that process? Meaning, if we wanted to find the antiderivative of x to the nth power with respect to x, so dx. Well, to reverse that, you now need to take care of the fact that you multiplied your exponent out front and then subtracted 1 from it. So to go backwards in that process, we take care of the fact that we subtracted 1 first, because that was the last thing that we did in that process. Whatever happened last needs to be taken care of first to reverse it. So, because we subtracted 1 from the exponent, the first thing that we have to do is add 1 to the exponent. So x to the n plus 1. And then because we multiplied the exponent out front as our first step, as our last step to reverse that, we have to divide by the new exponent. We divide by the new n plus 1 exponent. And then we always add plus c in case we lost some constant along the way. So again, the antiderivative of x to the nth power would be x to the n plus 1 divided by n plus 1. There is a quick note to make on this, and it's that n cannot equal -1. If it did, when you divide by n plus 1, you'd be dividing by 0, which is impossible. We will come up in the next video or two with a way to deal with that special case, and it should be pretty familiar. So remember one more time, we add 1 to the exponent, then divide by the new exponent. Whereas before we used to multiply the exponent out front and then subtract 1. We're reversing that process. So we'll go through an example together, and then I'll have you all try one. We have the antiderivative of x cubed dx. Again, always remember this dx is just telling us our variable. So x is the variable. We're finding the antiderivative of x cubed. So to find the antiderivative of x cubed, again, we start by adding 1 to the exponent, x to the 3 plus 1, and then we divide by the new exponent. So by 3 plus 1, and with that, we always put plus c, because we don't know if there was a constant in the original function. Simplifying this, we get x to the 4th over 4 plus c. And that's it. We don't have to put any type of notation. That capital F of x isn't necessary, especially since we weren't given that this is f prime of x in particular. All we do is, just like our notation when we had d dx, we just circle our final answer, the final expression. So we get x to the 4th over 4 plus c. Now before we try that example, I want you to take just a moment, maybe consider pausing the video, and think about how we could check if this is the correct answer. How could we prove that this is the antiderivative of x cubed? Pause the video for just a moment, try to think this through. Okay, so hopefully what you came to the conclusion of is if this x to the 4th over 4 plus c is the antiderivative of x cubed, then the only way that that would be true is if we take the derivative of x to the 4th over 4 plus c, we should get right back to that x cubed. If we don't, then something's wrong. This isn't the antiderivative. So let's check if we do. If we take the derivative of x to the 4th over 4, we have to multiply our exponent out front and then subtract 1 from it. So we multiply the 4 out front, which gives us 4x to the 3rd divided by 4. Remember, we don't need to use the quotient rule because the 4 is just a constant in the denominator. If it were a variable, we would need the quotient rule. And from here, the derivative of plus c, well, the derivative of any constant is just 0. And at this point, 4 divided by 4 will cancel out, leaving us with just x cubed, which is exactly what we started with. That means we have, in fact, found the correct antiderivative, because its derivative brings us right back to the beginning. You can always do this to check if you have the correct work, and the correct solution, that is. Okay, so from here, again, go ahead and take a moment to pause the video, try to see if you can solve the integral of 1 over x to the 5th dx. Alright, so from here, the first thing that we need to do is notice that we have a variable in the denominator of our fraction. That means we would be reversing something like the quotient rule, which we haven't talked about how to reverse yet. But we don't technically need to leave that in the denominator. Remember, we could always move this up to the numerator and give it a negative exponent. So this integral is the same thing as x to the negative 5th dx. If we were to move it back down, we'd get 1 over x to the 5th, so we haven't changed the problem, and now that we have this as just x to some power, we can find its antiderivative. And its antiderivative says we take x to the negative 5th, and remember, we add 1 to the exponent, and then divide by the new exponent, and add c. We always add 1 to the exponent, and then divide by the new exponent. So simplifying, we get x to the negative 4th over negative 4 plus c. And there's a couple of things we can do to simplify this. First of all, we should get this negative out of the denominator. We should never leave a negative in the denominator, so we'll bring it up to the top, which gives us negative x to the negative 4th over 4 plus c. And finally, we need to get rid of the negative exponent by bringing that x down to the denominator, but the negative will stay in the numerator, which will finally give us negative 1 over 4x to the 4th plus c. Remember, when we move the x to the negative 4th down to the denominator, that negative has to stay in the numerator, and there's technically a 1 in front of that x if we don't put it there. There's always a 1 there, so we're left with negative 1 over 4x to the 4th plus c. And again, if you wanted to check if this were correct, all you would have to do is take the derivative. We could do that from this step really quickly, just to check our work. If we multiply this negative 4 out front, we'd have negative 4 times a negative gives us positive 4 times x to the negative 4 minus 1. Remember, when you take a derivative, you subtract 1. So we'd get 4x to the negative 5th over 4. The derivative of c, well, the derivative of any constant, again, will always be 0. So that just goes away. And simplifying, the 4's cancel out, leaving us with x to the negative 5th, which is exactly what we have in our second step. We could simplify it down to 1 over x to the 5th, but clearly we have found the correct answer. So always remember, take the time to check your solution. It's always worth making sure that you found the correct one before you submit this on an exam. Alright, from here, we have one last fact to go through for this video. And then in the next video, we'll go through a little bit more of the more complicated rules that come up as we go through the basics of antiderivatives. So the last thing we need to introduce here is that the integral of k times f of x dx. So all we're doing is multiplying k into what we originally had in our last few problems. If we have the integral of k times f of x dx, then that will be equal to k times the integral of f of x dx. In other words, if you have a constant K has to be a constant. It cannot be an x or a variable or anything like that. If you have a constant being multiplied inside of your integral, it is always okay to multiply it to the outside of the integral. Meaning, take your antiderivative and then multiply that result by whatever constant you started with. This cannot happen if you are adding or subtracting the constant inside of the integral. In the next video, we'll talk about how to handle that. This is only for if you are multiplying by that constant. So with that in mind, let's find the antiderivative of negative 3x to the negative third all over 2 dx. The first thing that we should do here is find the constant. If there's any constant in this problem, we need to take it to the outside and then multiply it to our final answer. Notice we have a negative 3 being multiplied to our x, so it's tempting to say that negative 3 is the constant. But we are also dividing by a 2. Dividing by 2 is the same thing as multiplying by 1/2. So that is still considered multiplying by a constant. So when we pull out the constant, we have to pull out the negative 3 and the 2, or the division by 2. So when we rewrite this problem, we end up with negative 3 over 2 times the integral of all that's going to be left in here is x to the negative third dx. You could do a quick check to make sure you pulled the constant out correctly. If you multiply negative 3/2 by x to the negative third, you would get right back to negative 3x to the negative third all over 2. We could quickly show that over here, just to be safe. Negative 3 over 2 times x to the negative third. Well, we'll put this x to the negative third over 1 and multiply straight across, which gives us negative 3x to the negative third over 2 times 1 is 2. And indeed, that does bring us right back to the original problem. So always check along the way if you're unsure whether you made a correct constant pullout of these problems. So going back to this step, negative 3 over 2 times the integral of x to the negative third dx. Well, now we can just take the antiderivative of x to the negative third. So I'm going to bring an arrow over here to show where we're picking up. So we have negative 3 over 2 times the antiderivative of x to the negative third. Remember, we take x to the negative third, we add 1 to the exponent, and we divide by the new exponent, negative 3 plus 1, and then we add our constant c. We'll start simplifying this. So we have negative 3 over 2 times the integral of x to the negative 2 over negative 2 plus c. And when we distribute this negative 3 over 2, we get negative 3 times x to the negative 2 over 2 times negative 2 is negative 4. And then negative 3 over 2 times c gives us minus 3 over 2c. We have a little bit more simplifying to do from here. Note that we've already found the antiderivative. This is just algebra that we're simplifying at this point. A negative divided by a negative will give us a positive divided by a positive. It's the same result, that is to say, if you divide two negatives, it's the same thing as dividing two positives. And then from here, we can move that x to the denominator because it has a negative exponent. So we get 3 over 4x squared. And now here's the tricky part. Minus 3 over 2c is the same thing as plus c. Now you might be thinking, wait a minute, that doesn't sound right, that's impossible, everything I've ever learned in math has said you cannot do that, that minus 3 over 2 matters. But as it turns out, because this c value is constant, because it's not a variable, it doesn't matter if we put a minus 3 over 2 in front of it, or a minus 500, or a plus 1 million times that c. At the end of the day, it is still just some constant that we haven't accounted for. So no matter what you multiply to this c value, you can always bring it back to c immediately. Meaning we didn't even have to show this step where we distributed negative 3 over 2 to the c. It will always just be plus c. It sounds odd, but in our next few videos, either within section 6.1 or 6.2 or 6.3, we will go through an example where it actually shows why this is the case with a more rigorous explanation. But for the time being, just know that no matter what you multiply or divide this c by, as long as it's just a constant being multiplied or dividing by that constant will have no effect. Because this is not a variable, it will always remain the same value. Alright, with that in mind, this video is getting a little longer than I intended, so we'll leave it with just this last example. Go ahead and take a moment and try this out. Pause the video and then we'll try it together. Okay, so the first thing that we want to do here is take the constant out of the problem. So notice what's being multiplied to our x to the 5th here. We are multiplying by a negative 1, and we are dividing by a 6, which is the same thing as multiplying by 1/6. So we take out negative 1/6 from the problem. Because it's a constant, it can always be taken out, which gives us negative 1/6 times the integral of x to the 5th dx. And now from here we can take the antiderivative of x to the 5th. So we have negative 1/6 times the antiderivative of x to the 5th is x to the 5th plus 1. We add 1 to the exponent and then divided by 5 plus 1. We divide by the new exponent. And always remember, we get a plus c for whatever constant was lost when we took the derivative. So, from here, we start simplifying. We have negative 1/6 times x to the 6th over 6 plus c. We'll then distribute this negative 1/6. But remember, when we multiply it to the c, it will have no effect. It will remain c, which gives us negative 1 times x to the 6th is just negative x to the 6th. Over 6 times 6 is 36 plus c. And one more thing that might help you comprehend why we don't need that negative 1/6 there. Again, this is just some constant value, this c. So a way to think about it is if we had started with plus c1, meaning some c value that we'll call c sub 1, then it still would have been c sub 1 in this step because we haven't done anything to it. But when we distribute that negative 1/6 to it, it's now c sub 2. It's a different c value, but at the end of the day, we're still just solving for whatever number is being added or subtracted, so it doesn't matter what's being multiplied there. It is still just some constant value added to the outside. Again, it's perfectly okay if that step isn't making much sense. It will be more, it will make more sense in the next few videos.